Okay, I just hope we are all fine. Uh, Today I want us to solve one of the questions from a 2025 test paper. This was a deferred test 2. 2025 deferred test 2. Okay, and the question reads: ethylene oxide is produced by oxidation of ethylene as per the following. So the equation, the chemical reaction equation is given to be C2H4 reacting with 1/2 O2 to produce, this is C2H4 and then this is O. Okay, and the question reads: fresh feed containing ethylene and air is mixed with recycled feed and mixed with recycled feed, and mixed feed enters into a reactor. The proportion of ethylene to oxygen to nitrogen is in mixed feed is 1 to 0.5 to 5.65 on more basis. 50% per pass conversion is achieved in the reactor. The product gases leaving the reactor are fed to the absorber where only all C2H4O, this is the product formed, is removed. The gases from the absorber containing ethylene, oxygen and nitrogen are recycled back. To avoid buildup of nitrogen in the system, nitrogen is an inert. To avoid buildup of nitrogen in the system, small portion of recycle stream is continuously paged based on 100 moles per second ethylene in mixed feed. Okay, so the basis has been given. Then we are being asked to calculate the fresh feed to the process. Roman numeral 2, calculate the page stream. Roman numeral 3, calculate the recycle stream. Roman numeral 4, calculate the combined feed ratio. Roman numeral 5, determine the overall conversion of ethylene. So this is from a past paper 2025 deferred test. It is one of the examples I gave these guys in class when I was teaching this course. Okay, let us see how we are going to analyze this question. Let's see how we are going to analyze the problem. So first of all, we have chosen our basis. The basis has been given to be 100 moles per second. 100 moles per second of what? Of ethylene, which is C2H4 in mixed feed. Okay, that's our basis. Now let's proceed. We draw the process flow sheet. Okay, just like I explained in class, this will be drawn like this. Okay, where we're going to label this as the reactor. That's the reactor. And from the reactor, we are going to have another process unit, which in this case, it is an absorber. But in most cases, they use a separator, but this time around they decided to use an absorber. Okay, now from this absorber, we are being told there are two streams coming out of the absorber, where this stream contains only the product. Contains only the product. And then from the absorber, we also have this stream. Okay. We have that. We have this. So now this is the recycle stream, but we are being told to say a fraction of the recycle stream was what? Paged. Okay. That's the page. Okay, at this point, so we not say we have a mixer at that point, of which degrees of freedom analysis, I have already done that, and this problem can be solved. Okay. Okay, at this point, let's try to put data now. So we're being told to say fresh feed containing that and that is mixed with recycled feed. So the fresh feed here, we say F as the fresh feed. This fresh feed contains ethylene, like that, and it also contains air, of which I'll use air. Now remember, in class I said air is a mixture of gases which is made up of 21% oxygen and 79% nitrogen. So I will not write it in form of percentages, but I'll write it in form of more fraction, which is 0.21 of oxygen and 0.79 of nitrogen. So this is the composition of air. Okay. Now, at this point, this is the fresh feed that we have. All these things makes up the fresh feed only. Then now, at this point, we have this to be the recycle stream. Then we have this to be the page stream. Okay? We have that to be the page stream. Then now we're being told to say, with recycled feed and mixed feed enters into a reactor, the proportion of, okay, so at this point, this is the mixer. After the fresh feed together with the recycled stream has been mixed, then it is fed to the reactor. Now, let's try to find the composition of the mixed feed that is entering the reactor. So this has been given. The ratio has been given to be 1 to 0.5 to 5.65. So just like I said in class, here we are going to have 1 plus 0.5 plus 5.65, which gives us a total of 7.15. That's a total. So meaning from here, we have 1 out of 7.15 to be ethylene. Okay? Of which this will be 1 divided by that to give us ethylene to be equal to 0. My space 0.14. Okay, I didn't consider enough space here. That's 0.14 for ethylene. Let me just write it here so that I won't forget. This is ethylene 0.14. Okay, meaning we are also going to have oxygen to be 0.5 divided by 7.15, which gives us oxygen to be equal to 0.0. This is 7 when you round off, 0.07. So it's the same as us writing it here, 0.07. That's oxygen. And what is remaining here is the nitrogen. So the nitrogen will be 5.65 0.65 divided by 7.15, which gives us 0.79 for nitrogen. 0.79. Okay, so this is the composition of the mixed feed. This is the composition of the mixed feed. Now, we proceed and read. We've been taught to say 50% per pass conversion. Yeah, I explained what pass conversion is. I also explained what overall conversion is. Okay, I know you know that. 50% pass conversion is achieved in the reactor. The product gases leaving the reactor are fed to the absorber, where only, okay, I'm not looking for this. There is a basis. I'm looking. Where is the basis? That was a statement which she gave us. Okay, based on 100 mole per second of ethylene in mixed feed. Okay, so we are basing our calculations on 100 moles of ethylene in mixed feed. Just this ethylene, 100 moles per second. So now, how can we determine the total flow rate if we know the composition of ethylene? The job is easy. So it is just, let's say, the mixed feed M, meaning that we're going to have 0.14 of M. Okay, 0.14 of M. I just hope you can see 0.14 of M is equal to 100 moles per second. 100 moles per second, which gives us 0.14, 0.14, like that. Meaning the mixed feed is equal to 714.29 moles per second. So this is the sum of the mixed feed, fresh feed plus the recycle feed, which is 714.29 mole per second. So now this is the amount of feed that is entering the what? The reactor. Meaning at this point, it is easy for us to determine how much nitrogen is going into the reactor. Okay? And it is also easier for us to know how much oxygen is going into the reactor. That will be easily known. Now, we've been told that it is 50% pass conversion. 50% pass conversion. Now, when you look at the stoichiometrical ratios of this balanced equation, it is a 1 to 0.5. A 1 to 0.5. So what does this mean? We have 100 moles of ethylene going into the reactor. Now, how many moles of oxygen do we have going into the reactor? So moles of oxygen, we are going to have 0.07 by 714.29, which gives us 50. Which gives us 50 when we round off, which gives us 50 moles per second. Okay? Gives us 50 moles per second. This is the amount of oxygen that is entering the what? The reactor. Such that if we were to find which one is the limiting reagent, you will discover that when you divide 100 divided by 1, 50 divided by 0.5, this gives you 100, this gives you 100. Okay? Meaning the stoichiometrical proportions are equal. So meaning, in this case, we can consider oxygen and we can also consider ethylene. Both of them were completing at the same time. Okay. So now we're being told to say it is 50% pass conversion. 50% pass conversion. So meaning only 50% of ethylene will take part in the chemical reaction. Meaning if 50% of ethylene takes part in the chemical reaction, then 50% of oxygen will also take part in the chemical reaction. What does that mean? That means that we are going to have 50 more per second of ethylene reacting. And we are also going to have 25 more per second of oxygen gas that is reacting. That's what it means. Okay, then from the reactor we are going to have products, which will be the main product being produced, which is C2H4O. That's the main product. The excess ethylene, the excess oxygen, nitrogen. Okay, that's all. These are the products that we are going to have. Okay, so at this point we will know, just like I explained in class. I said you consider the stoichiometrical ratios in the chemical in the balanced chemical equation. So when you look at it, it is 1 mole of ethylene to 1 mole of the product. So meaning if we reacted 50 moles of ethylene, meaning we produced 50 moles of the product. So we are going to have 50 mole per second of the product. Okay, that's hope it makes sense. 50 mole per second of the product. That is what is being produced. Meaning what is remaining here, ethylene, we are remaining with 50 mole per second of ethylene is remaining. Then for oxygen, we are remaining with excuse me. For oxygen, we are remaining with 25 mole per second. Oxygen. But remember that in this chemical reaction, nitrogen is not taking part. So the amount of nitrogen that is entering into the reactor is equal to the amount of nitrogen that is leaving the what? The reactor. So let's calculate how much nitrogen is entering the reactor. We have 0.79 by by 714.29, which gives us 564.29 mole per second. So this is the amount of nitrogen that is going in, that is entering the reactor, and it's equal to the amount of nitrogen that is what? Leaving the reactor. Thank you. Yeah, I have a cough. Okay, then we're being taught to say when these products enter the absorber, all of the desired product is absorbed. So meaning the amount of product that goes into the absorber, it is equal to what will come out. So here we are going to have 50 moles per second of this product. Then the rest is being recycled. So meaning we are going to have C, which is ethylene, we have oxygen, we also have nitrogen. That's what it means. Okay. Now, here we must find the total of the products being what? Recycled. The total, which will be what? 564.29 plus 25 plus 50. This gives us a total of 639.29. That's the total. 639.29 as the total of the amount of product that is being recycled after the desired product has been absorbed. So we are having that. Meaning, I don't want us to express these results here in terms of the moles, but I want them to be expressed in terms of more fractions. Meaning that we are going to have 50 divided by the answer, which gives us 0.078, okay, of ethylene. Then we are going to have 25 divided by 639.29, which gives us 0.039. Okay. Then for nitrogen, we have 564.29 divided by 639.29, which gives us 0.883. Okay, I'm just rounding off. my values. Okay, 0.883. So this is the combination, this is the composition, sorry, this is the composition of the product, the amount of product that is being recycled. That's the composition. So now you should know to say when this product reaches at this point, this is a separator here. Maybe, yeah, it's a separator, definitely. So when it reaches, it can be a separator or a splitter. Okay, any of the two. We're not told in the question. So it can be a separator or a splitter at this point. So at this point, when this stream is being splitted, the composition isn't changing. Okay, that must be understood. The composition won't change, but the amounts might change. Definitely will change, because the amounts will have to add the amount that goes through this stream plus what goes through this stream to give us what is coming into the splitter. But the composition doesn't change, it will remain the same. What does it mean? This means that in the page stream here, in the page stream, we are still going to have C2H ethylene to be equal to 0.078, oxygen to be equal to 0.039, nitrogen to be equal to 0.883. The same is in the recycle stream here, the same composition. This won't be affected, it's not changing. Okay, having understood that fact, now we proceed. Let's do a component balance for nitrogen. Okay, so how much nitrogen is entering? So my component balance will be based on the overall conversion, because when I use single pass conversion, we will have difficulties. But the best approach to this problem is to use an overall conversion. So overall conversion meaning what goes in is equal to what is going out, as usual. Now you discover that this nitrogen is an innate, so it is not present in this stream, it is only present here. So the amount of nitrogen entering at this point is equal to the amount of nitrogen that is leaving through the page stream. So for nitrogen, this will be 0.79 of A. Remember, A is the air. 0.79 of A to be equal to this will be equal to 0.883 of P. That's what it means. So this can be our first equation. Let's also see a component balance for oxygen. Oxygen component balance for oxygen. Oxygen, it's also 0.21 of A. That's the amount of oxygen entering. 0.21 of A to be equal to, this is equal to the amount of oxygen present in the product here. Now, just like I explained in class how to get the amount of oxygen when oxygen is present in the product, just do the same thing. So meaning here we are going to have oxygen to be equal to 25 moles per second. That's the amount of oxygen that is present in the product stream there. This will be plus 0.039 of P. So we have accounted for all the oxygens that are present in the chemical process. Okay, so at this point now we have two equations which are promising to be solvable. So let's solve. Let's just make A, the subject of the formula. That will mean our A, which will be is equal to 0.883 of P divided by 0.79. This gives us what? Gives us 0.883 divided by 0.79. This gives us 1.1177, okay, of P. So we have our A to be equal to that. Meaning in the second equation, while there is A, we will replace with this. So we replace, we are going to have 0.21, 1.1177P to be equal to 25 plus 0.039 of P. Okay, this will be times 0.21, which gives us 0.2347. The number continues of P. Then we subtract minus the 0.039. This gives us 0.1957 of P equal to 25. Then we divide by 0.1957, then there by 0.1957. This gives us P to be equal to 25 divided by the answer. We are getting 127.73 more per second. Okay, so this is the page stream. So page stream is equal to 127.73 more per second, of which we have already answered the second part of our questions. Okay, at this point, let's proceed. We answer the first question, because the first question is asking us to determine the fresh feed to the process. Okay, so at this point we have our we have our what? We have our page stream to be equal to this, meaning we can easily determine how much air was being fed. So how much air will be determined by using this equation or this equation. So we have air entering to be equal to 127.73 divided by, multiplied by 1.1177. This gives us amount of air entering to be equal to 142.76. Okay, now I am not interested in the amount of air entering, but I am also interested in the amount of oxygen entering. So the amount of oxygen entering will be equal to this same figure by 0.21, which gives us 29.98 more per second. So the amount of oxygen present in the fresh feed is 29.98 more per second. Okay, now if we have it like this, okay, if we have it like this, we know the amount of oxygen that was entering through the fresh feed. So I'm just doing this so that you are able to see what we can do in case we are being asked to determine the amount of oxygen that was being fed, in case we are asked to determine the amount of air that was being fed. But the actual question has already been evaluated. We have already solved the problem. Having established the page here, 127.73 more per second. So we know to say, at this point, we know to say fresh feed here, the fresh feed will be as a sum of, the fresh feed, just want to show you something. Fresh feed will be equal to the mixed feed minus the Mixed feed minus the what? The recycled feed. Because we know that recycle plus the feed will give us the mixed what? The mixed feed. That is true. That statement is true. But now, how is this recycle? Where is it coming from? You can agree with me that P is equal to recycle plus, what I meant, the P is for the page, but let me just label this part as T. Okay, meaning that we not say T is equal to recycle plus what? Plus P. And the T is known to be 639.29. Remember, we found this one. So we subtract minus the P, which we got to be 127.73 to give us the recycled feed. So we're going to have 639.29 minus 127.73 to give us the recycle to be 511.56 mole per second. So that's the recycle. We have also answered, which question was this one? We have also answered question 1. Calculate the recycle. We have also answered the third question here. We are being asked to calculate the recycle stream. It's answered here. Then now, since we know the recycle and we know the mixed feed, we'll just say how much was this mixed feed? The mixed feed was 714.29 minus the recycle, which is 511.56, which gives us fresh feed to be equal to 714.29 minus the answer, which gives us 202.73 202.73 more per second. 202.73 more per second. So this was the fresh feed that was what? That was being fed. And then the page stream has already been found. The recycle stream has already been found. So this is the first approach you can use to approach this problem. But if you are not comfortable with this approach, you can use you can consider the carbon atoms only. You can consider the carbon atoms, so that you see how the carbon atoms are performing, and you can still get the answer, the same answer, just by considering the carbon atoms alone. Yes, that also would give you the correct answer. Otherwise, we end here. Just in case you want to join us, to join our tutorials, you can contact 09675 73759. Name of the tutor, it's Shikwesha. That's the name of the tutor. You can just inbox us, so that you can just text us, call or text, so that we get to move together. Otherwise, see you in the next video.